Okay, here are your notes on testing and graphing solutions. The first thing we're going to discuss is testing solutions to equations. So we know that a solution to an equation, if I go too fast, feel free to pause me or rewind me, but I don't want to waste anybody's time, so I'm going to try to book it through this, okay? Is a number that makes the equation true. All right, so here's what we do. We have an equation, 2x minus 1 equals 7, and we want to know if 4 is a solution. So one of the fastest ways to figure this out is to test it by letting 4 be the x. So 4 is going to be the x. We are going to put the 4 in for the x. So that will be 2 times the 4 minus 1 is 7. And we want to know if that is true or not. Okay, so 2 times 4 is 8. Minus 1, is that 7? Well, yeah. 8 minus 1 is definitely 7. 7 equals 7. This is most definitely true. So because this is true, we say 4 is a solution because it made my equation true. It's as easy as that. Okay, next one. For number 2, we want to know if 4 is a solution to this other equation. So we're going to do the same thing. We're going to take 4, we're going to let it be x, and plug it in. So we'll have 2, and then times of 4 plus 3, that's plus. Does that equal 11? Now, PEMDAS tells me that I have to simplify stuff in parentheses first, if I can. So I have a 4 plus 3 in parentheses. That makes a 7. So I have 2 times 7 equal to 11. Now, hopefully you're like, ooh, that looks weird, because 2 times 7 is 14. And we know that 14 most certainly does not equal 11. So this statement is false. It's a contradiction. So we say that 4 is not a solution. And we can say that because it made the equation false. Okay. Now we get to talk about graphing solutions. So whenever we graph solutions, we are going to shade, that's an S, shade the values that make the equation true. Okay, these values that make the equation true, these are our solutions. So we're going to shade the solutions. All right, here's an equation that we have to solve and then graph the solutions by shading. So we have parentheses here, and if I look at the x and the negative 5, I can't combine those like I just did with the 4 and the 3 in parentheses. The 4 and the 3 were like terms. The x and the negative 5 are not like terms. So I have to do something else to get rid of parentheses. I am going to distribute. Hopefully you remember that. So I'm going to distribute the 3 to the x, and I get 3x. Distribute the 3 to the negative 5, multiplying, and I get negative 15 equals negative 12. Now I'm trying to get x alone to find out what it is. So I want to add 15 to both sides. I'm trying to get x alone over there. So the 15, the negative 15, I'm getting rid of it. A negative 15 and a positive 15 cancel. That gives me 3x equals 3. Now, 3x is a multiplication. They're multiplied together. It's 3 times x. And I know that to undo multiplication, I have to divide. So I'm going to divide by 3 over here. And if I do it to that side, I have to do it to the right side. Now something interesting happens here. 3 divided by 3 is 1. Put it in your calculator if you don't believe me. 3 divided by 3 is 1. And I know that 1 times x is just x. Same thing happens over here. 3 divided by 3, it's 1. So I get x equals 1. Okay, so when you're graphing, you don't have to do anything too fancy. Just show me where 0 is, show me 1, and then show me that you know that negative 1 is on the left side of 0. Okay? When I look at these directions, it says we shade where it's true, right? Well, 1 is the only value that is going to make my equation, whoops, I wrote EG, not EQ, my equation true. So if I put 1 in for x, the equation will be true. Any other number, false. So the only number I'm going to shade is 1 with a solid dot. That's how I shade 1. Okay, next one. I'm going to leave this where you can see both for a second. I want you to be looking at 3 and 4. Look at 3. You see how I had 3x on this step right here. When I had 3 in the numerator, I needed a 3 in the denominator to make a 1. I need that same thing to happen on number 4. Problem is, I'm starting with a 3 on the bottom. So if I put another 3 on the bottom, they're not going to go away. What I need is a 3 on the top. So I need a 3 up here. So I'm actually multiplying by a 3. That's what's going to give me my 3 over 3 that's going to turn into that beautiful 1. Okay. So if I multiply the left by 3, I multiply the right by 3 as well. Okay, when you multiply fractions, you go straight across. 3 times 1 is 3, right? And then I have a 3 on the bottom, 3 over 3. We said that's 1. That's the whole reason we picked 3. So we have 1 times z equals negative 6. 1 times z is just z, so I see that z is negative 6. So when I graph this, I'll show you where 0 is. Here's positive 6, and negative 6 is to the left of 0. And I will use a solid dot on negative 6. Okay, I don't know how to change the page. Oh, got it. Oh, I tried to figure that out for 10 minutes earlier tonight and felt like a goofball. Wasn't so bad. Okay, now we're going to do the same thing for inequalities. First of all, we can make an inequality when an inequality symbol, that's a Q, quality symbol is placed between two expressions. Okay, so this first symbol is greater than or equal to. So you can see right here, equal. And you can see in the symbol, there's an equal sign kind of hybrid meshed in there. Okay. If you flip back to the front of your paper, you'll see that when we had an equation with an equal sign, we used a solid dot. Well, this one gets a solid dot too because it has an equal sign in the symbol. Solid. Geez. Solid. Okay. The next symbol is the less than or equal to symbol. It also gets a solid dot. Because it has an equal sign smushed in it. Third, this is the strictly greater than symbol. We're going to use an open dot. Oh, that was huge. An open dot. So an example of this type of situation would be like if you're going out to eat and you're trying to order from the kids menu, they're not going to let you because you are greater than 12, right? So you are not going to be able to eat from that menu. Okay. Here we have a less than symbol. What I should have said, but I didn't because I was tired and my brain wasn't working, is that if you're greater than 12, which you are, you have to eat from the adult menu. You don't get to eat from the kids menu. That's 12 and under. So if you're greater than 12, you get the adult menu. I said it backwards and I'm really sorry. Okay. Hopefully that didn't confuse you. Less than. Another open dot. Okay. Testing solutions to inequalities, we're going to do that the same way we do with equations. We are looking for a number that makes the inequality true. So any number that makes an inequality true is a solution. So we're going to test 2. So we're taking 3 times 2 minus 1. We want to know, is that greater than 5? So 3 times 2, that's 6. 6 minus 1, that's 5. Is 5 greater than 5? Hopefully you're saying, no, 5 is equal to 5, so it can't be greater than 5. So this is false. So 2 is not a solution. Oops. because it made the inequality false. Okay, just like with equations, for graphing solutions to inequalities, we will shade the values that make the inequality true. Remember that the values that make it true are these solutions. All right, let's look at this first one. We cannot combine the x and the -1 because they are not like terms. So do not combine those. You'll make the math gods angry. You have to distribute this 2 to get rid of these parentheses. So we get 2 times x, that's 2x. 2 times -1, that's -2. Okay, we're going to get rid of the -2 here by adding 2 to both sides. These cancel. So I have 2x is greater than or equal to -6. Now I'm dividing by 2. And I get x is greater than or equal to -3. So looking at my symbol, I can tell that I need a solid dot. So I'm going to show you where 0 is. Here's +3. Here's -3. I'm going to put a solid dot on -3. And then I want to shade greater than. So does everybody agree that $3 is greater than -$3? So I'm going to shade to the side that has the +3 because the +3 is bigger than the -3. And then I'm going to shade the arrow to show that my shading goes on forever because it's not just 3 that's bigger than -3. 4, 5, 6, 7, 8, a million, 5 billion, those are all bigger than -3. All right, I'm going to show you a little trick to check your work. If your variable is on the left, watch what happens. Boop, 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 boop. Do you see how they point the same way? That's how you can tell you did it right. It will not work if your variable is on the right. You need the variable on the left to use that trick. Okay. All right, for number 7, I want you to look back at number 4 that had the 3 on the bottom. When we had that 1/3, we needed to multiply by a 3 to get a 3/3 to make a 1. Here we don't have a 3 on the bottom, we have a 5. So instead of multiplying by 3, we will multiply by 5. And if we multiply by 5 on the left, we have to multiply by 5 on the right. So this gives me a 5/5. W is less than 10. Now, the magical part is that 5/5, just like 3/3, is 1. 1 times W is W. So my W has to be less than 10. All right, I'm going to show you where 0 is. I'm going to say 10 is over here. -10 is down here. By looking at my symbol, it's a less than symbol, so I need an open dot. Put open dot on 10. This time, I'm shading less than, so I'm going to shade to the left. Don't forget to shade the arrow, because all of those numbers off to negative infinity are less than 10. Okay, here's your trick to make sure you did it right. Look at the symbol. It should point the same way as your arrow. Okay, I think that's a wrap. I'm going to bed.